Hey all, welcome to diverging lenses, concave lenses, ones that bow inward. This will help you with ray diagram back worksheet, ray diagram back, worksheet. Diverging lenses. Okay, so what does the diverging lens do? It makes the light spread out. What happens is, for your definition, all rays of light that enter parallel to the principal axis will converge? No, diverge. Goodness gracious. Diverge from a focal point on the near side of the lens. So rather than the rays converging to a focal point on the far side, they're going to diverge from a focal on the near side. So here goes the light, here goes the light, here goes the light. And what it does is it bends, and then by the time it bends the second time, it bends away from a focal on the near side. So, and again, nothing is random in physics. Those rays on the right are diverging straight away from the focal on the near side. As if I drew a line like this, that dashed line, and I said it's going straight away, straight away, straight away, straight away. Whoa, that was rough. Let's fix them. Okay. Straight away from the focal on the near side. So those are diverging lenses. When do you use diverging lenses? Not a whole lot. But what's kind of neat about like your eyeball is the eyeball is a little bit of a combination. The eyeball is round on the outside, but it's not just like that. Like the wall of the eye kind of looks like this, right? So if the wall of the eye looks like this, it's really kind of like a converging lens next to a diverging lens. Kind of cool, right? So the inside would be concave, but the outside is convex. Convex means it bows outward. The inside means it concave means it bows inward. So we're understanding the two different types of lenses individually. You got convex converging lenses, which make the light converge to a focal on the near side. And then you've got concave lenses, which make it diverge from a focal on the near side, rather. So again, converging from our notes the other day, converging, all rays parallel converge to a focal on the far side. For diverging, all rays entering diverge from a focal on the near side. Okay, cool. So what kind of images would we get from this? Let's go with our same rule, or same kind of little experiment here for ray diagrams. What we're going to do is we're going to take a principal axis. We're going to draw our diverging lens. And just for comparison, I'm going to use the exact same numbers I used the other day for converging with my same tree, just to show you how the image is different. So I'm going to even say that the object distance is 60 centimeters. We're going to use the same math. My focal is 20 centimeters, but now it's diverging. I'm even going to say the height of the object is 40 centimeters to see what that does. Now, how do I locate this image? Well, we use the ray diagrams to kind of imagine where the image is. We're trying to locate the image. So if I take a ray and go parallel, rather than going over here to the focal on the far side, it's just going to diverge from a focal on the near side. So there goes my ray. I know that any ray straight through the middle from the top of my object, I can get a straight edge and just go straight, straight, straight. Straight through the middle, goes on forever. Any ray right through the middle of the lens goes on forever. Okay, there's two rays. Boy, those are not coming together. I got some concerns for what's happening on the right side. Yikes. So first ray, parallel, away from the near focal. Second ray, right through the middle. The third ray, again, is a reversal of the first. The third ray is a little bit tricky. I'll draw in red. I'm going to go towards that far focal. Here I go towards the far focal, but it never makes it. What it does is it comes out parallel. Because if I ran that in reverse, I'd go parallel, 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 and away from the near focal on that side. Got it. So here's the concern. These three rays didn't come together. That's a problem. I don't know where my image is going to be if they don't come together. So what I do when they don't come together is I trace them back. So here's the lens. Let me make it in blue. Here's the center of the lens. What's happened on the right is what I want. What's happened over there on the right, where they spread apart, is actually what I want, but I need to fix it. If I trace them back, trace those three backwards, that's where my image is going to be. I'll do another one here in just a second. If you ever have rays that spread out or move away from each other, they don't come together, they don't converge on their own. Trace them backwards from the lens, each of the three, these three. Trace them straight backwards from the center of the lens right here, and you'll find your image. So again, my first ray, parallel, 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 and went up this way. My second ray went right down through the middle, and my third ray went to the far focal, but came out parallel. Those three black lines didn't come together. But then what I did is I said, I'm going to trace each of those three straight back, and that's where my image is going to be. We call this a virtual image. Virtual. That means versus what happens over here, this is a real image. The light rays are actually converging to that point. They came together on their own. This is not a real image, it's a virtual image. Virtual images are where the light rays aren't converging on their own. I kind of have to make it happen by bringing them back into like negative space. Okay, so how do I solve for DI and the mag and the height of the image? Well, you know your equation, but we got to make an adjustment. Why do we have to make an adjustment? Because my image didn't end up upside down over here the way it did in the last lesson, right? My image ended up kind of in a weird spot. It's not over there at 30 centimeters. But if I do the same math, I'll end up with the exact same answer. So there's got to be a difference. When you're doing diverging, one thing changes. Since we're using the focal on the near side of the lens, not the far side, we're using a different focal. That focal is on the negative side. It's on the near side of the lens. You'll have to remember for diverging lenses, when you do the math, to get it right, that focal has to be negative in your equation. So now, if I do 1 over negative 20 equals 1 over, nothing else changes. Still positive for the DO. Everything else is good. The only change is that guy has to be negative. When I do that, 1 divided by negative 20 minus 1 divided by 60, 1 divided by second answer, I get negative 15. Well, that makes sense. Because if you look at my image, check out my image, which is kind of busted at this point, but here it is. The focal is right here. Remember, the focal lengths are 20 centimeters from the lens. So check out that negative 15. Negative, I'm back on the same side. 15 centimeters, I'm a little bit more than halfway back. That'd be 10. And there's where my image is, exactly where I think it should be, even with a pretty rough diagram. So my image distance is actually negative 15 centimeters. Watch my mag. My mag, nothing changes, but it's negative DI over DO. Well, what does that mean? Negative 15 over 60. Well, the negative is going to be positive, so 1/4 or positive 0.25. What does that mean? That means positive, the image is upright. There it is. If the tree is up here, oops, make it green. My little tree is upright over there. It's not inverted over here, negative. It's upright. It's also smaller. That's the 0.25. So what's the overall height then? 10 centimeters. And how did I get that? If this is 40, my mag is 0.25, my height is 10. Okay. I need to help some of you guys with the converging the other day. What if I have a converging? This is back to converging. There's one converging that's really nasty. What if I have a converging lens situation? And I don't think the math is the problem, but the image is hard. What if the ray diagram, what if my object is in here? This would be like a magnifying glass. A magnifying glass, you put your object inside the focal length. And what does it look like? Your images look big. if I take a magnifying glass and read letters, they look big, right? If I'm inside the focal. They look small if I look across the room. They look big if I'm inside the focal. The ray diagram is really tricky for this one. What if I go parallel, converging, parallel through the far focal? The second ray always goes right through the middle. Ooh, red flag. Those are not coming together. My third ray, I don't even know if I can do, but what it should do is touch the object, the near focal and the lens. That'd be like this, and then come out parallel. Yikes. These three are not coming together. So now that we understand diverging, when the three that pass through the lens, as they should, don't come together, what do? We trace straight backwards until they do come together. So if I look here at the lens, trace straight backwards. Straight back, straight back, straight back. What I end up with is an upright, big virtual image. Upright, big virtual image. So here I expect a negative DI. It's converging, but you're still going to get a negative DI. I'm going to get a mag that's positive and greater than 1. It's upright and it's big. And then my height's pretty easy to calculate. So when you get that converging where you're inside the focal, it's pretty tough. Treat it kind of like you're diverging. It's similar, but I still have to do the rules for converging, right? So again, one more time in blue, parallel through the far focal, that's converging rule. Straight through the middle, that's for everybody. The third one is near focal object lens, parallel. The three didn't come together. Now, like diverging, I can trace backwards from the lens, and my image ends up being back over here. So really kind of cool ray diagrams help us see. That's like looking through a magnifying glass, and you see a virtual big image. Hope that helps. That's ray diagrams front and back, converging and diverging lenses. I'll see you guys soon.